So here we go with our we're halfway through college algebra, and we're starting the second 9 weeks here. And I really want to encourage you guys to really pay attention to the material in these podcasts. Make sure, like this one, there is so much information in here, exponential functions, that you really need to make sure that you understand the material. So no going through this fast. Make sure that you understand this, slow it down, and yeah, I know it's boring, but you guys have to do whatever you need to do to understand this material. So if you're going through this fast, just thinking, oh, this is an easy way to do homework, this is not going to help you at all. So I really need you to slow down. At the end of this podcast, you're going to have some problems that I expect you to know how to do when you get done with this podcast. And if you don't know how to do them, you know what? You probably need to go back and listen to it again. All right, so let's really work hard. Let's end with a bang here so that everyone, I know it's a lot of work, but then everyone will feel good about the grade, that they really worked as hard as they could and did everything they could to get a good grade in college algebra. And that takes some work. All right, so let's go to this first slide here. And let's just look at what an exponential function looks like. So you see that the variable is in the exponent. So it has f of x is equal to a to the x. Now it says we're only going to consider functions where the a is a positive number. All right. And also it cannot equal 1. And if you look down here, it says 1 is excluded, because if we put in a 1 for the a, then 1 to any power is always 1. So that's not an exponential function anymore. If f of x is equal to 1, that's just a constant function. And that would look like a horizontal line 1 unit up. So that is not an exponential function. So we can't have a 1 for a base. We cannot have negative numbers. That's just not something we deal with in college algebra. But we might have a base of a fraction, like a half. So, yep. I'm going to write it like this. F of x is equal to 1/2 to the x. We could have f of x is equal to 4 to the x. So those are exponential functions. And just like all our other functions, we could take those functions and shift them left or right. We could shift them up or down. We could flip them over the y-axis. We could flip them over the x-axis. We could stretch and shrink them vertically and horizontally. So all of those same ways that we dealt with that with quadratics and absolute value and all the other functions, it works the same way for exponential functions. All right, let's start off with graphing f of x is equal to 2 to the x. So once again, the values that we plug in for x are the exponents. 2 is raised to that number. So let's just do a table of values. And let's take the values -3 through 3. Just looking at integers for right now. Okay, so the first one, if we're going to let x equal -3, then we're trying to evaluate for the y then. We want 2 raised to the -3 power. Well, a negative exponent, we make it positive by bringing the whole power down to the denominator. So we get 1 over 2 to the third, and 2 to the third is 2 times 2 times 2 or 8. So this is equivalent to 1/8. Okay, let's take 2 and raise it to the -2. So we want to make that a positive exponent. So we go 1 over 2 squared then. And 2 squared is 4. So we get 1 over 4. 2 to the -1 is 1 over 2 to the first. 2 to the first is just 2, so we get 1/2. Okay, 2 to the 0, Well, anything to the 0 power is 1. 2 to the first is 2. 2 to the second is 4. And 2 to the third is 8. Well, that gives us quite a few points then. So let's go ahead and graph those. I'm going to start with 0, 1. So 0, 1. And then let's go to negative 1. Negative 1 is 1/2. Negative 2 is 1/4. Negative 3 is 1/8. So what's going to happen as I go to the left is I put in smaller and smaller numbers for x. The number itself, when I take 2 and raise it to the power, it's getting smaller and smaller. But it's never going to equal 0. So 2, there's no power that we can raise 2 to get 0. And there's no way we're going to get a negative number either. Okay, so it is approaching 0 there. And then let's do 1 when x is 1, y is 2. Then we have the point 2, 4, and 3, 8. Okay, so if I draw through those points and make a smooth transition between those points, this is my exponential function here. So it looks something like this. Okay, now we're going to take a function that looks just a little bit different. We have f of x is equal to 2 to the negative x. Let's pick the same x values that we used in that last one. Okay, so I did negative 3 through 3. Did all the integers. Okay, so let's start off with negative 3. So 2 raised to the opposite of x. So if x is a negative 3, we want to take the opposite of it, so that will make it a positive 3. 2 times 2 times 2 is 8. Okay. So we're putting in a negative 2 for the x. The opposite of negative 2 is positive 2, so we want 2 squared, which will give us 4. This will be 2 to the positive 1, which is 2. Here we get 2 to the 0. Anything to the 0 power is 1. Now we're putting in a positive 1. So it says take 2 to the opposite of your x. So we need 2 to the negative 1. And remember, we just did that in that last graph. So we're going to make that exponent positive by bringing it down to the denominator. So we get 1/2. Here we're going to get 2 to the negative 2, which is 1 over 2 squared, which is 1/4. And then 2 to the negative 3, which is 1/8. Now those numbers look familiar, but let's see what happens when we graph here. Now we have negative 3, 8. We have negative 2, 4. Negative 1, 2. 0, 1. 1, 1/2. 2, 1/4. 3, 1/8. So here it's just going the opposite way. So we're going to connect those. And you want to make a curve out of it. Here again, this is approaching 0. It's going to get closer and closer to 0, but it will never equal 0. Okay? Now, keep in mind then that this graph here, we had a negative in for the x, And before, when we talked about functions, we said if we have like a function f of x, and I put a negative in front of it, we said that would be a reflection in the x-axis. Whereas if I put a negative in for the x, that would be a reflection in the y-axis. And you know, if you remember back to the graph that we just did, it looked like this. And those two graphs, that first one with the graph and this one, do represent a reflection in the y-axis. And notice up here I plugged in a negative x for the x. So this is a reflection in the y-axis. Okay? Now we're going to compare those two graphs a little bit. So here I have the blue one and the red one. So can you tell me, do you remember what the equation for the blue one was? Notice I have the point 0, 1. I have 1, 2. I have 2, 4. And we have 3, 8. And negative 1, 1/2. So this one, negative 2, 1/4. So the blue graph, the equation was y is equal to 2 to the x. Okay? Whereas the red one is where we put y is equal to 2 to the negative x. Okay, now I'm going to change that just a little bit. I am going to rewrite that, and we're going to look at it like this. We're going to say y is equal to 2, and we're going to break apart the negative x, and we're going to say that's equivalent to negative 1 times x. Would you agree? Negative 1 times x gives us negative x. Now we're just going to look at 2 to the negative 1, that quantity raised to the x. Okay, so that's the same thing as that last one we did. So a power to a power, we multiply the exponents. So if I want to get rid of the parentheses here, we'd take negative 1 times x, and we get back to negative x. Well, what did we just say 2 to the negative 1 was? Well, we said 2 to the negative 1 was 1/2. So now I'm going to replace that 2 to the negative 1 with 1/2 to the x. Now take a look at those two. Notice that we have a decreasing function here, the red one, when the a is less than 1. So if it's a number between 0 and 1, so if the a value is less than 1 but greater than 0, then we have a decreasing function. And it's decreasing over the whole domain, which is all real numbers. Okay, so let's write that down, the domain, and then we'll take a look at it, see if that makes sense. So the domain is negative infinity to infinity. So if I go anywhere along here, if I pick an x of a 0 or a positive number or a fraction or a negative number, I see that there is a point above it. There are no gaps or breaks or jumps in this graph, so it's continuous. So therefore the domain is all real numbers, negative infinity to infinity. Okay. The same thing is true with the blue graph though, but instead of being a decreasing function, it is increasing over the whole domain. And the domain of this one is the same thing. The blue one doesn't have any gaps or jumps either. So the domain is we can plug in any number for the x and raise 2 to that power. Okay? So there's no restrictions on what we use for a number in an exponent. So the domain is all real numbers, just like in the red graph. However, in this one, to make it increasing, that a value has to be greater than 1. All right, so for example, we might have like y is equal to 4 to the x, or y is equal to 5 to the x, or y is equal to 1.1 to the x. As long as that a value, that base of that power, is greater than 1, it's going to be an increasing function. And then likewise, if we go over to the red one, if the a here is between 0 and 1, so like 2/3, oh, I better use red. So if I have y is equal to the 2/3 x, or y is equal to the 0.9x, or y is equal to the 1/5 x, then it's a decreasing function, and it's going to look like the red one. Okay, so remember, our exponential function look like this. Okay, so we're looking at that value of a. If it's more than 1, it's going to look like the blue graph where it increases. If it's less than 1 but greater than 0, it's going to look like the red graph and decrease. Now let's talk about the range, what the y value is. Well, remember I told you it's never ever going to cross that asymptote. It's never going to equal 0. It's never going to be equal to a negative number. So that means our range, let's take a look at the red one then. The only y values you're going to have are positive numbers. All of these points on here, the y value is a positive number. So that means our range is 0 to infinity. But it doesn't include 0, so I don't have a bracket with the 0. Okay? And let me go ahead and write down. It is continuous. I can draw the whole graph without picking up my pencil. And it does have a horizontal asymptote at y is equal to 0. So the x-axis is the asymptote, and it is for both of the curves. So that same thing applies over to our blue curve. It also has a range of 0 to infinity. It is also continuous, and it also has a horizontal asymptote at y equals 0. So these two graphs have a lot in common. The only difference, one is increasing, one is decreasing. Okay. Now, like I said, these graphs, then we can apply those same transformations that we did to our absolute value and square function and cubic functions and square root functions. So let's just take this one here. The blue graph had the equation y is equal to 2 to the x. Okay, so keep in mind our table of values then when we graph this, I'll put it up here this way, is when x is 0, 2 to the 0 is 1. When x is 1, 2 to the first is 2. If x is 2, 2 squared is 4. X is 3. 2 to the third is 8. So those are some points on that graph. 0, 0. 1, 2, 2, 4, 3, 8. Okay. Now, let's say that we were going to take that function and let's do black. Okay, let's say we're going to look at the graph of y is equal to 2, and embedded inside the function, up there in the exponent, we're going to put a -1 with the x. Okay? Well, when it's embedded inside the function, that's the horizontal shift. And that horizontal shift goes just the opposite. So instead of going to the left one, it goes to the right one. So if I take each of these points that we had here, like 0, 1, and I go 1 over to the right, I end up with the point at 1, 1. If I take the point 1, 2 and go 1 over, I get 2, 2. 2, 4 becomes 3, 4. 3, 8 becomes 4, 8. Negative 1, 1/2 becomes 0, 1/2. And then this is a 4th, and this is an 8th. So this is what our curve looks like. The only difference is it has been shifted to the right 1 unit. It's just to the right one. Okay. If I kept the same base, kept the 2 to the x, but all I did then is put a plus 3 at the end of it, then what that does is it takes every one of our y values and it moves it up 3. So this point here, the 0, 1, is now at 0, 4. Up 3 units. Okay, this point here at 1, 2 is now 1, 5. 3 units higher than the one in the blue. This point here goes up to here. This point here goes up to here. And we could go back over here. This point here, 1, 2, 3, it's going to be here. This point here is going to be here. So notice now what this looks like. Our horizontal asymptote has changed. It is now 3 units higher. So our curve is getting closer and closer to the line y is equal to 3. But this one then, with that plus 3 at the end, is moved up 3. Okay? And once again, we have a horizontal asymptote on this one. Instead of the y-axis, or I'm sorry, the x-axis, it's at y is equal to 3. So it's getting closer and closer to this line instead of the x-axis, because everything is shifted up 3. Okay? And then let's say that we're going to take a number. I'm going to have to use blue. I don't have too many options for colors here. Let's say that we take y is equal to, we've got our 2 to the x, and what we're going to do is we're going to multiply it times a number. So we're going to put a number out to the front. Now remember before, when we had like an absolute value or something, that's what changes the slope of it. So this one then, with that times 3, we're taking every y value that we had and we're multiplying it by 3. So this point here at 1, 0, I'm sorry, at 0, 1 is now going to be 1 times 3. It's going to be up here. This point here, that's 1, 2, we take the y value, 2 times 3. So 2 times 3 gives you 6. So we're going to be up at 6. So we're stretching it vertically by 3. The point here, 2, 4, we take the 4 times 3. So now it's at 12. The point that was here at negative 1, 1/2, 1/2 times 3 is 3.5. Or 3, I'm sorry, is 3 halves, or 1.5. Okay. And if I take the negative 2, 1/4, if I take that times 3, I get 3/4. Well, maybe about there. So here's our curve. We're stretching it vertically. So notice how the curve is much sharper. Okay, so all of those same transformations still apply to exponential functions. Okay, let's talk about exponential growth. Let's say Windsor is growing at a rate of 3.2% a year. And according to the 2005 Census Bureau estimates, the population of the town back in 2005 was 14,874. So we are interested in Windsor's population in 2010. Okay, so let's start off with the table. So X is going to represent the year. Y is going to represent Windsor's population. Okay, so in 2005, we were at 14,874. Okay, so if it's growing at 3.2% a year, then to figure out what the population was in 2006, we could take the population from the year before and multiply it times 0.032, right? And that'll tell us how much growth we had. But then to figure out what the population is, we'd have to add that number on to the 14,874. So instead of doing that in 2 steps, we can do it in 1 step by simply multiplying by 1.032. So once again, that's the same thing as multiplying it by 0.032 to get the growth and then adding it back on. And you can try that. You'll see that either way we get the same thing. Okay, so if I multiply that out then, I came up with 15,349. That doesn't look much like a 3. There we go. All right, for 2007 then, we would take that population that we had before, so the 14,874 that we had multiplied by 1.032, which gives us this number, and we would take that then and multiply it by 1.032 again. So I'm going to write it here as we're multiplying it by this quantity squared. All right, does that make sense? So to go 2 years beyond 2005, I'd have to multiply that base population of 2005 times 1.032 twice. Okay, so to get the population in 2008, which is 3 years down the road, we'd have to multiply it by 1.032 to the 3rd power. Seeing a pattern here? So if I want to figure out then the population in 2010, well, 2010 is how many years after 2005? Well, it's 5 years later, so we'd have to multiply our population from 2005 times 1.032 to the 5th. Okay, and these populations, if I fill them in here at 2007, I came up with 15,841. Here I came up with 16,348. And here I have 17,411. Okay, so from that then, if I want to know any year, so let's say that it's going to be T. So any year after 2005, I can take the 4,874 times 1.032 to that number, the number of years since 2005. So here's our formula for exponential growth. To get the amount, we take the initial amount or the original amount, and you'll see they like to use a sub O. And so if we're looking for the population, then we say, well, our beginning population, so A sub O, times 1 plus the rate. So remember here, 1 plus the rate was 3.2% a year, so that's 0.032. And we added those together, and then we raised it to the number of years since 2005. So that's our formula for exponential growth. All right. Now, similar to that then, we have exponential decay. Let's take a look at this example. So Frank has been monitoring the parking lot for 10 years now. And the number of parking accidents, let's say, was 32 in 1999, so back when he first started. So if the number of accidents is decreasing at 5% a year because of him being so good out there, how many total accidents will we have this year in the parking lot? Okay, so let's do a table again. So the X is going to be the year. The Y is going to be the number of accidents. Okay, so let's start in that first year. Frank started 1999. We had 32 accidents. Okay, then the next year, in the year 2000, we had 5% less. All right, so 5% less means that we would take the number of accidents, so 32, times 5%, and then subtract it off. Okay, so remember how in that last one we went 1 plus the rate? Well, because we're decreasing, now we're going to go 1 minus the rate. And if our rate is 5%, and 5% is a decimal, is 0.05. So if we're decreasing by 5% a year, that means we're actually we're keeping 95%, or we're having 95% of the accidents that we did the year before, right? So it's less than 100% because it's decreasing. So instead of going 1 minus 0.05, let's just go 0.95, and we'd raise it because it's that next year, just times 1 to the first power. Okay, and then if you do that and round it, I got about 30 accidents then. Okay, so in 2001, we'd have to take that answer that we just had in the last one, but instead of showing it as 30, I'm going to show it as 32 times 0.95, and then we take it times 0.95 again. So we're taking it times 0.95, or 95%, twice in a row to get 2 years beyond 1999. And if I round, whoops, I get about 28 accidents. Okay, 2002. I'm taking that last value, which we got, by taking 32 times 0.95 to the second, and I multiply it times 0.95 again. And that is approximately 27. Okay, so we want to know how many total accidents will we have this year. Well, this year is 2009. 2009 then is 10 years from 1999, so we're going to raise it to the 10th. So you need 32 times 0.95 caret 10, and you can try that on your calculator. I got 19. Okay, so this is exponential decay. So it's a lot like our exponential growth. The only difference is, to get the amount left, we take the initial amount times 1 minus the rate raised to the t. Okay, so that's the only difference, a plus or a minus, between growth and decay. So if it's growing, it's more than 100%, and if it's decaying, it's less than 100%. Okay? All right. Whoops, I lost one. Let's go back here. Compound interest. Okay, let's say Kyle has $2,400 he wants to put in savings, and he wants to keep it in the bank for 2 years, but he's got a dilemma. He's not sure where to go. Bank of Colorado is offering 4% interest compounded quarterly, while Chase is offering 3.8%, but they're compounding it monthly. Okay, well, unlike simple interest, compound interest means that they'll figure the interest during at each of these compounding periods and then throw that interest into your account, where if it's simple interest, they won't. So let's kind of compare the two. Let's put Bank of Colorado here, And we'll put Chase over here. So let's think about this formula then. So for Bank of Colorado, we know that we're starting off with $2,400. Okay. And we know then it is offering 4% interest. Okay. So just like 4%, that means they're adding it on. So we take 1 plus the rate. However, they are compounding it quarterly. Quarterly means 4 times a year. They are figuring how much interest you have made and they are throwing it into your account. So if you get 4%, that means you get 4% for the whole year. Okay, so if they figure your interest after the first quarter, then you only get 1/4 of that interest. So you only get 1%. So what they do is they take your rate, and instead of just multiplying it by 0.04, because they're doing this 4 times during the year, they have to divide it by the number of compounding periods in a year. And we've got 4 compounding years, 4 compounding periods because it's compounded quarterly. Every 3 months, they're going to give you some interest and throw it into your account. So now this has to be raised to the time. But the time is not just strictly 2 years because they are doing this interest 4 times a year for 2 years. That means they're doing it 8 times. So this becomes 8 instead of 2. All right? And if you multiply that out, so in your calculator, you'd want to put those parentheses in there. So you want 2,400 parenthesis 1 plus 0.04 divided by 4 in parenthesis, and then caret 8. I get 2,598.86. So that's how much money you would have in the bank at the end of those 2 years. So that doesn't mean you made that much money. You started off with 2,400. So if you subtract 2,400, you actually made $198.86 in interest. All right. Well, let's see what Chase has to offer. So we start off with the 2,400. This time we're getting 3.8%. So they're adding it on. So it's 1 plus the rate. But this one now is compounded monthly. So instead of doing this interest thing 4 times a year, they're doing it every month. So that means they're doing it 12 times a year. So they're going to take your interest, which is 0.038, and divide it by 12. And every month, that'll tell you how much interest you make then, 1/12 of the yearly rate. And then we got to raise it to the number of times that they do that. Well, if you're keeping it in the bank for 2 years, but you're compounding it monthly, then that means how many actual pay periods do you have? Well, you have 12 times 2, so you have 24 of them. Okay. Now, if you will plug that into your calculator, see if you agree with what I got. I got $2,589.20. So it looks like you should go with Bank of Colorado. Okay. Now, let's write this down then. There is a special formula for finding compound interest. And you need to know for the compound interest, you need to know how many compounding periods you have in a year. Is it compounded quarterly? Is it compounded monthly? Or is it compounded daily? Or something like that. So we've got to know for n compounding periods. Every year. Okay? So the formula is, to get the total amount in your account, you take what you originally invested, so the principal, times 1 plus the rate, divided by the number of compounding periods in a year. Remember here, this one was compounded quarterly, so we divided by 4. This other one was compounded monthly, so we divided by 12. And then you raise it to the NT. So on this one, we took 4 times 2. And on this one, we took 12 times 2. So the N's are the number of compounding periods in a year. So on the monthly, it's 4. I'm sorry, on the quarterly it's 4, on the monthly it's 12. If it were daily, then you use 365. If it is semi-annually, then you'd use 2. That means twice a year. All right, so it's per year. So there's the formula for compound interest. Now let's take a look at some examples. I hope you guys are still hanging with me, so if you're getting a little tired of something, please pause it, get up, move around something, and then come back, because you need to be fresh. You need to be able to apply these examples. All right, so here we go. Use the graph of f to describe the transformation that yields the graph of g. So here's my f. F of x is equal to 3 to the x, so that's the parent function. So how is this graph different? Well, the minus 2 is embedded inside the function with the x, so that gives you the horizontal shift. And because it's a minus 2, it means it is shifted to the right 2 units. Okay? On this one, our parent is f of x is equal to 1/2 to the x. So on this one, oh goodness, what's going on here? Well, there's a negative in front of the function. And remember, a negative in front, like if this is my parent function, y is equal to x squared, and if I put a negative in front, do you remember what that does to it? Or if I have y is equal to the square root of x, and then I look at y is equal to negative square root of x, remember that flips it over the x-axis. So that's what that negative is doing there. So it's reflecting it in the x. Axis. But then I also have that 4. So if I think of this as just a plus 4, it's an additional 4. Notice it's at the front, but it's the same thing, right? So 4 minus that, or the opposite of that plus 4, it's the same thing. So what does that mean if you have a plus 4 at the end? That means that it is also up 4 units. Okay, so there's 2 transformations going on with that graph. Take a look at 3. How is this graph different from the parent function g of x is equal to 4 to the x? Well, I've got a plus 3 embedded inside, so that means it's going to be left 3. And then I have a minus 2 at the end, so that also means then it is going to be shifted down 2. Here is a function, and notice it's an exponential function because I have my a is 1/2, and it's raised to the negative x, and we want to evaluate it, so we want to fill in this table. So we've got the function 1/2, and we're going to plug in a negative 2 in for the x. Well, it says take the opposite of x, so the opposite of negative 2 is 2, so we want 1/2 squared, and then after we do that, we want to subtract 3. 1/2 squared, well, 1/2 times 1/2 is 1/4. So 1/4 minus 3 is negative 2 3/4. And yes, you can do that on the calculator if you need to. Okay, let's plug in a negative 1. Well, the opposite of negative 1 is positive 1. So 1/2 to the first is 1/2. Minus 3. So that's negative 2 1/2. Okay, plug in the opposite of 0, where the opposite of 0 is just 0. 2, or 1/2 to the 0 is 1. Anything to the 0 is 1. And 1 minus 3 is -2. Okay, how about the first power? So we have 1/2 raised to the -1 and then -3. Okay, so what that means then, I have this whole fraction raised to a negative exponent. So to get rid of that negative, since it's a fraction, we flip the fraction. So it's 2/1 to the first. Anything to the first power is itself. So 2 divided by 1 is 2. 2 to the first is 2. 2 minus 3 then is -1. And then let's do it with the 3. So we're plugging in a -3 now. Okay, so we want to get rid of that negative exponent, so we flip it again. So it's going to be 2/1 to the positive third. 2 divided by 1 is 2. 2 to the third, or 2 times 2 times 2 is 8. And then 8 minus 3 is 5. Okay, so here we filled in the function, then that's what we need. Another way you could do that is to plug it into your graphing calculator and then evaluate it. Okay, that would work good also. Evaluate the function for the given value. Now this is where you do have to use your calculator. And so make sure when you plug this in, like our function here, f of x is equal to 3.5 times 1.03 caret, and then your whole exponent is x divided by 2. So what you're going to want to do is put parentheses around this whole exponent. So you're going to have 1.3 caret, parenthesis, 145 divided by 2. Okay, so you have to plug it in there like that. And I want you to pause this and try that, see what you come up with. And I will put the answer, I will write the answer here. So make sure and pause it right now because I'm getting ready to write it down. Okay, the next one, same thing. When you plug it into the calculator, you're going to need 2 times, or you can put parenthesis pi, and then you're going to put caret, and then parenthesis 4 times 0.8395. So you want to make sure and have the 4 and the x all in the exponent. So make sure and put parentheses around it. Okay, so pause it because I'm going to write down what I got. All right, so if you didn't get that 93.4, try it again, please. All right, now here we want to solve these equations for x. We'll take a look at these equations. Our variable is in the exponent. Oh my, so what we can do here is notice over here we have 2 raised to the 3x minus 1, and here I have 8, which is a power of 2. So we're going to take the easy way out then. We're not going to do anything to the left side. And over here, we're going to replace 8 with 2 to the third, because 2 to the third is exactly 8. So they're the same thing. So I can use substitution. Now I have powers on each side, and they already have the same base. They already have a base of 2. So the only way they're going to equal is if their exponents are equal. So I'm just going to set 3x minus 1 equal to 3 and then solve it from there. So add 1 and then divide by 3. So 4/3 will be our value for x. Okay, so notice the variable is in the exponent, so those are exponential equations, and we just get the same base and then ignore the bases. Okay, so on this one, take a look here now. I've got a 1/5 and I've got a 25. Those are our bases, 1/5 and 25. So you think, well, what can I use for a base that I could raise both of them to a power to get those two numbers? Well, that 5 is probably jumping out at you. 1/5 happens to be 5 to the negative 1. And that whole thing is raised to the x plus 2. On the other side, 25 is 5 squared. So see, we're using a base of 5. Okay, over on the left side, though, it's a power to a power, so we keep the base the same, and we simply multiply the exponents. So we need to take negative 1 times the quantity x plus 2. Well, that'll give us negative x minus 2. Right? You're distributing that negative 1 to both of those values. Now notice I have powers on both sides with the same base. They both have a base of 5. So we're going to ignore that base and just set the exponents equal. So if negative x minus 2 is equal to 2, then I'm going to add 2 and then divide by negative 1. So negative 4. Same thing on this last one here. I don't know if you can read this. It's 6 raised to the 0.2x. So 6 to the 0.2x. Okay, that already is a power with a base of 6. Over here I have the cube root of 6. Well, I can use the 6 as the base of the power, and then if I take it to the cube root, that's equivalent to doing the 1/3 power. So now I have powers with the same base, so I ignore the base, I ignore the 6, and set 0.2x equal to 1/3. Well, 0.2 is 1/5. And I can either divide both sides by 1/5 or multiply by the reciprocal. In this case, it's going to be easier to multiply by the reciprocal. So x is 1/3 times 5, which is 5/3. Okay, so you've got a lot of work ahead of you here. Here are the problems I would like you to do before you come back to class. Okay, so you're going to have to pause this and write these down. Try those problems. If you get stuck, I encourage you to go back and look at the podcast again. Okay, so be accountable for what you are learning. All right, there we go. See you soon.